All right, good morning. It's Friday, April 17th. And anyway, this is our regular Zoom meeting. And we are going to basically go over sample means. The notes are fairly short, but there's several problems. Many of the problems are actually challenging out of this group. And I chose those not to scare you, but just because I feel like it may help prepare you for the long 25-minute questions. Today we're going to go through the notes, and once we get through the notes, we'll do 2 FRQs on Tuesday of next week, which will be our next Zoom meeting. We'll also do 2 FRQs. I have to leave that meeting early, so it'll only be from 8 o'clock to 9 o'clock, because at 9 o'clock I have a meeting with district. And then we will finish the remaining 3 problems on Thursday of next week. Please note there is a Stats Saturday tomorrow. I hope you will join us. I think it'll be very beneficial. We'll be going over units 3 and 4. If you have an opportunity, it'd be really great if you got the Stats units 3 and 4 before Saturday. But if it's not a requirement. Just might be helpful. All right, so with that said, let's get started. First off, when it comes to sample means, there's a lot of pages in the notes file. You can see it's 113 to 132 in Unit 1, which basically introduces the t-test. And then it's pages 133 to 171 in Volume 2. I would highly recommend you tab all your recipes. I may try to do something kind of nice, but I haven't had time yet. Since y'all are going to have access to things during the exam, I may try to get some things set up that might make things easier to locate. Study the last 2 pages of Volume 2, because that's where you can find formulas and conditions. I don't have a good way to put this on a document camera. Your last 2 pages, I have it turned sideways, have all the conditions, all the formulas, and that would be easy, quick access, since this year they're allowing you to utilize notes, etc., during the exam. So that would give you quick access and might be very beneficial to you in the middle of the exam. All right, so the t-test. In particular, the t-test is also a mound-shaped symmetric test. Looks like the normal. The only difference is it's flatter and has more area in the tails. And for every sample size or every degrees of freedom calculation, it becomes closer and closer to the normal. It never is normal, but it becomes closer to the normal. All right, it is symmetric and centered at 0. So basic formula, and when can you use the t-test? You use the t-test when you don't know the standard deviation of the population. So if you don't know the standard deviation of the population and you're having to rely on the standard deviation of the sample, you use the t-test. Now, one of the requirements is the underlying distribution has to be normal, or they will either tell you that, or you'll have to draw a box plot to show it, or some other graph to show it, or the sample size must be 30 or larger, in which case it becomes normal by central limit theorem, or approximates the normal by central limit theorem. Let's see. If the data is not symmetric and your sample size is 30 or more, you can go ahead and use it. You're good to go. And one of the key words to knowing when to use it, as opposed to sample proportions, if it talks about means, that's probably a good hint that we're going to be using a t-distribution. And once again, the reason you use it as opposed to the z-distribution, which is looks very similar in formula, is the formula for the z is going to look like z equals x bar minus mu over sigma divided by square root of n, is because here I had the population standard deviation, and for a t-distribution I did not. Okay? All right, so couple example problems, or A test of hypothesis, HO mu equals 0, alternative mu is greater than 0 was calculated using a sample of size 7. The test statistic was 1.935. So what is the p-value? I'm going to turn around and grab a sheet of paper real quickly. And so first thing, I always like to draw that little picture. I already know the t statistic is centered at 0. They give me a 1.935, and I need to find that area. All right. And I know I needed to shade up because the alternative hypothesis said greater than, so that's why I shaded up. And the other thing that I need to note is my sample size was 7. For a one sample t, the degrees of freedom is n minus 1. So in this case, 7 minus 1 equal to 6. So quickly, or maybe not so quickly, second vars, TCDF, the lower bound is 1.935, the upper bound is infinity. My degrees of freedom are 6. I didn't even have to worry about the standard deviation. It's not part of it. So I get a 0.05057. I'll check that real quickly. Okay. All right, moving on. The next one. A botanist collected one leaf at random from each of 10 randomly selected mature maple trees of the same species. The mean and the standard deviation of the surface areas for the leaves in the sample were calculated. So right here, they tell me they're working with a mean, which indicates I'm going to be working with X bar in some form or fashion. And then they tell me the standard deviation was calculated from the sample. So that lets me know that I'm utilizing a t distribution. So assume that the distribution of the surface of the maples is normal, but I had to tell me it was normal because my sample size was less than 10. Less than 30. So it's because I have a sample size of 10, which is less than 30. I needed to know it's normal, or I needed to put together a box plot or a dot plot to show that it was normal. Since they gave me no data, I couldn't do that. So they needed to let me know the underlying distribution is normal. So what is the appropriate method for constructing a one sample confidence interval to estimate the population surface area of the species of maple leaves? All right, so I want to talk about a couple of these answer choices and why they're wrong. The Z is appropriate because the sample standard deviation is known. The Z would have been appropriate if the population standard deviation is known, but since it's the sample standard deviation, that's false. All right. The Z is appropriate because the central limit theorem applies. First off, Z isn't appropriate because the central limit theorem applies. Z is only appropriate if we know the standard deviation of the population. And the central limit theorem doesn't apply here because our sample was only 10, it wasn't 30. So that's false for two reasons. Okay. The Z interval is appropriate because the Z interval is narrower than the T interval. That is a true statement. The T interval, the Z is narrower than a T interval, or the T has more area in the tails. But again, that's not a reason. That's just a fake answer they put out there. It's your fake news. The T interval is appropriate because the T interval is narrower than the Z interval. First off, that's false. The T interval has more area in the tails, so basically that can't be true. The T interval is appropriate because the population standard deviation is not known. All right, so once again, the population standard deviation is not known, so therefore the T interval is appropriate. So anytime you're using the sample standard deviation, you should be thinking about a T. All right, so that's your basic T, and then we move over to paired. I spent just a little bit of time with some examples on this because we get confused sometimes between when to use a paired test and when to use a two sample T. So the paired test looks at the difference between paired values. In other words, it's comparing two values so that you're going to have a mu D or because you went x minus x, not x bar, but x minus x. It should have been subtracting two x's. And typically speaking, we're looking at a before and after type situation. In paired t-test, we calculate the differences of each pair. In do so, we have taken two samples and created a single sample. So formula-wise, this looks very, very similar to a t-test, because a t-test just had this formula. A paired t-test is going to be the average of the distance differences for the sample minus the population differences over the standard deviation of the differences divided by the square root of n. So really, I added these to indicate that I'd taken two values and subtracted them. Now, most of the time, if not all, the mean of the paired will be 0 because you're expecting there to be no difference, right? That's typically what happens, but not always. Okay, paired data is extraordinarily powerful, and you should use it anytime you possibly can. And why? The reason is it controls for differences between the pairs. Remember the mosquito problem. Some people are more susceptible to mosquito bites. So consequently, it'd be great if I could test people twice because it controls for differences within each individual. All right? And even though the sample isn't independent because the same person got tested twice or the same thing got tested twice, the differences are, because however many bites I got should not impact how many bites you got. So the differences is not between how many bites I got, because those are definitely dependent, but between the individuals that are being tested. All right. And once again, we typically use paired data for a before and after situation or something that got tested twice. All right. Degrees of freedom for this is n minus 1, but the n is the number of pairs. So the number of pairs minus 1 gives me my my degrees of freedom. All right. Big caution. This is one of the things that we struggle with. If data is paired, we do not take the mean of each sample and then compare the means. That's a two-sample test for means, which is what we're about to talk about. So a two-sample test for means. Just a two-sample t-test, and we're looking to see if there's a difference between the means of the two groups, and et cetera. And then we compare. Basically, at that point, we take all the values of one group and all the values of the other group, and we calculate two separate averages. So we're having two separate means and we're comparing them. That's opposed to taking the individual values, subtracting them so that we have one. All right, so here we have two means versus a paired only having one. So I have a couple different problems that I switched up so they look somewhat similar, but one will be paired and one will be two sample. And I'm hoping that as we discuss this, or as I talk about this, some of it might be might help you to determine which it is. So in this case, a manufacturer claims its Energizer battery lasts longer than its competitor's Duracell battery. 9 batteries of each brand are tested independently, and the hours of battery life are shown in the table below. Provided that the assumptions for inference are met, what type of tests should be conducted to determine if Energizers do, in fact, last longer than Duracell batteries? Well, they needed to tell us the assumptions were met because we don't know if the underlying distribution is normal, and we'd hate to sit there and have to make a box plot for this, but they're basically saying, hey, everything's good, you can go ahead and do this. And I look at this, and I'm like, you know, anytime I see data links that are exactly the same thing, the very first thing I want to think is this could be a paired data test. I don't know if it is, I don't know that it's not, but it could be paired because the data links are the same. And then I have to sit there and go, well, would it make sense to subtract these two? And it's like, it could, and I'm a little bit stuck, and I'd like to go ahead and tell you the answer, but I think it'd be better if I rolled into the next problem and did it first and then go back up here, because I think we'll see a difference between the two problems in the way they're set up that might be a big help. So looking at the problem below it, and by the way, it looks very much the same, except we added a different row. So let's see what the story says, or the scenario says. A manufacturer claims its Energizer battery lasts longer than its competitor's Duracell battery. 9 batteries of each type are randomly selected. From the 9, one randomly selected battery of each brand is tested on a randomly selected toy. So now I'm testing a battery from each brand on a toy. So toy A got tested by the Duracell and by the Energizer. And toy B got tested by the Duracell and the Energizer. So at this point, what I see here is I see that each toy got tested twice. And so here I know that they were tested twice. Because I know that they're tested twice, I know that I'm working with a paired distribution, right? So this would be a paired distribution here. So I could run a paired t-test. Now let's contrast that up here. Does it make sense to take a randomly selected battery from one group and compare it to another battery? And the answer is not, unless you're testing something. So basically, because I'm not testing this on something, I need to be testing the average of this one and the average of this one, average of Duracell and the average of X bar. The other thing that might help is they indicate independent. And to be a 2-sample test, and this is very, very important, the samples need to be independent. 2 independent random samples. Here, our sample is actually the differences between these, okay? Now, sometimes they'll give you a table where they calculate the differences, and that makes it easy. Sometimes the data are different lengths. If the data is different lengths, you can't run a paired. So, but here it was a little bit trickier because you have data of the same length, but you need to sit there and think to yourself, hey, was I testing this twice on something, or is this a before and after situation? I mean, if this had been before and after, then something was obviously tested twice, but not in this case. We don't know that anything was tested twice, and since they didn't provide that information, we have to assume that it's a two sample. All right, continuing on. Researchers used 2 footballs of the same size to examine the effect of helium on kicking distance. One football was filled with air, and the other was filled with helium. 11 people participated in the study. Each person kicked the football filled with air and the football filled with helium, and the kicking distances in yards recorded. The football that was kicked first was determined by flip of a fair coin, and the people did not know which football was filled with the air and which was filled with helium. What's the appropriate T interval? So we know we're kicking 2 footballs. My question is something being tested twice? And the answer is yes. And here's the hint. We have 11 people. So 11 people are kicking 2 separate footballs and measuring the distance. So consequently, because we have someone being tested twice, we can sit there and go, oh, this makes this a paired test because we have something being tested twice. And we know that because we have essentially person A, person B, person C, and then we have helium and air. So basically, the fact that I can make something out of it, basically making a 3-row person, where we have person A, B, C, and D, and then helium, and then air. That would and we have the same size, the same sample lengths. That makes this a paired. Now I'm going to contrast this with another football problem, because that's what we should be talking about during COVID, is football and big stadiums filled with people. But here we go. On a windless day, A member of a high school's football team is punting specialist, kicks two identical footballs, one filled with helium and the one filled with air, 10 times each. He alternates footballs and is not told there's any difference. The distance in yards of the kicks are recorded in the table below. And once again, I look at this and I go, well, set the same length. Was something tested twice? And the fact of the matter, it was not. We only have one person, so we have person A doing all of this. So this is X bar 1 and this is X bar 2. Had they said that instead of one person kicking it 10 times, they had 10 people kicking each one once, then it would be paired. Okay? Are there questions? Does that help a little bit with paired versus two sample? Because those are actually a little bit tricky, and I try to pick some tricky ones there. All right, so reason for the N is less than 10% of the population condition. A reason for N is less than 10% is so that that when you take something out and you don't replace it, it's not really independent. And I always like to think of my giant pile of M&Ms. You know, I have this massive, beautiful pile of M&Ms, and I sneak one out and eat it, and it happened to be a red one. Technically, the percentage of reds changed. But because it was such a huge pile, it changed so minimally or by so little that we didn't worry about it. So basically, we are essentially saying it's independent enough. So if N is less than 10% of the population, if the sample size is less than 10% of the population, then we don't worry about it. The fact of the matter is, at one point they cared about this, then for several years they didn't care about it. Now you absolutely have to have it. Now we've included it all year, so it shouldn't be a problem, but it's absolutely required. But if you look back at some of the old scoring guidelines, it wasn't required. All right. There is an exception for that. I should address that. If you're doing instead of doing a sample, you're actually conducting an experiment. You do not need to state it if you're conducting an experiment. If you do state it during the experiment, it's not wrong, so you don't have to worry about it, so you can be consistent, but it's not as important. All right, so when using a one sample T procedure to construct a confidence interval for the sample mean of a finite population, a condition is that the population size must be at least 10 times the sample. The reason? Sample size is large enough. Generally speaking, that's referring to proportions where NP and N times 1 minus P both must be greater than 10. The central limit theorem is applicable for the sample mean. Central limit theorem applies when N is greater than or equal to 30. So that's not this. And basically, I went through this problem just so that it would give us the opportunity to talk about these different ones. The sample standard deviation is a good approximation of the population standard deviation. That doesn't apply to this. And it is a reasonable approximation, but will not be the same. But that's not the reason. That has nothing to do with the 10 times. The degree of dependence among observations is minimal. That's very true. And the sampling method is not biased. That doesn't have anything to do with that, because sample size does not impact bias. Okay? So bias is in design of the experiment. Speaking of sample size, when we talk about confidence intervals, as we increase the level of confidence, the interval gets wider. So if we go from 90 to 99, I'm going to have a wider interval if I keep everything else the same. If we increase alpha, the margin of error decreases. And here's why. If we went from 0.90 to 0.99, we got wider. Well, this means my alpha was 0.1 here and my alpha is 0.01 here. So if I switch the order, then I'm going to get, then obviously my confidence level, because this is my alpha, my confidence level is tied directly to my alpha and vice versa. As the sample size increases, the margin of error or spread decreases. Not only does the margin of error or spread decreases, but the standard error increases, because the standard error is S divided by square root of N. Obviously, that gets smaller as N gets bigger. Margin of error just puts the T star in front. And so this whole thing will get smaller as N gets larger. Please remember that as you change sample sizes from one sample to another, it follows this formula as far as width. So let's just say we had an original sample size of 4,000, a new sample size of 1,000. I'll put that over 1. Now I have 1 over the square root of 1/4, which is basically square root of 1, square root of 4. So 1 over 1/2. So in this case, if I started with a 4,000 sample size and went to a 1,000 sample size, I got twice as wide. And basically that makes sense that I would get wider because this number got smaller, not bigger. Because I originally started with 4,000 and then I went to 1,000. All right, power. And by the way, I'm going to talk more about power and error, although I briefly discuss it here, we're not going to do much with it. But power and errors, we will discuss in greater length, not next week, but the following week when we talk about proportion. But we are going to look at it for just a little bit here. So power is the probability of rejecting a false null hypothesis. In other words, you did the right thing. You rejected the null and you were supposed to. All right? Power is 1 minus beta. And we can increase power by increasing alpha. And here's why that is. The area in the tail is alpha. As this number gets bigger, as alpha gets bigger, this thing scoots back. Obviously, my rejection zone got bigger. And the larger the rejection zone, the easier to reject. Increasing sample size also increases power. Probably one of the best ways to increase power is to increase sample size. Power increases the further a value is from reality, provided that it moves, the distance is in the direction of the alternative hypothesis. So if I'm too far to the left, my power increases because I have a less than. If I had a greater than, as I move to the right, my power increases. So, supposing a hypothesis test for a single mean, we have the alternative of mu is less than 10. Assume that HA is true. So basically they're telling us the null is false. And they didn't give us the null, but I would assume that the null is this. They're telling me already that this is 10. And they're saying this is false. So basically, this is a correct decision. The power of the test will be greatest if the actual mean is which of the following. Well, the farther I am away from reality, the greater my mean. Well, this one is 2 away. This one is 2 away. So they're equal distance away. However, that one is in the wrong direction. I had to be less than. So 8 is the appropriate answer. Now, just say, even if this had been 13, and that's actually farther away from the mean, it's in the wrong direction. The only one, the smallest one, or the value farthest away in the correct direction was 8. So power increases as I move away from the claim and I move in the direction of the inequality. Now, had this been a not equal situation, both 12 and 8 would have been equally correct, and you wouldn't have been able to make a choice, or you would have said both 8 and 12, okay, are possibilities. All right. P-value is the probability of getting a test statistic as extreme or more extreme. Just that simple. So at the end of the day, when we calculate a p-value, it's like, oh, we got a p-value of 0.03. So there's a 3% chance we'd get a test statistic this extreme in favor of the alternative when in fact the null is true. Or if you want to shorten it up, you can even say there's a 3% chance that we get a test statistic this extreme given that the null was really true. And at some point we sit there and go, I don't believe the null is true because the probability is too small. For instance, there's a 43% chance that we get a statistic this extreme if the null is true. Well, that happens a lot. That's almost flipping a coin. So that happens a lot, so could be true. On the other hand, there's less than a 1% chance that we get a test statistic this extreme if the null is true, or given that the null is true. Well, the fact of the matter is, I don't think I'm that unlucky. That's less than 1% of the time. So I no longer think the null is true. I have to believe something else is true. That's what that means. Okay, then we have our errors. Type 1 error is rejecting a null when we shouldn't have. The null was true, but we got a small p-value, we rejected, we shouldn't have. Why did this happen? Well, because we got a weird sample. That happens. It wasn't biased, okay? We're assuming that we didn't take a bad sample. It just, our sample didn't match the population. We did everything right. We put all the juniors, sophomores, seniors, and freshmen names in a hat, and we drew too many freshmen. Hopefully that doesn't happen to you guys. I think it did this year. That's why all the senior celebrations had COVID-19 and now are a little more difficult to have. Sorry about that, guys. So the way I would write my conclusion for type 1 is, in this case, the probability of rejecting the null, whatever that is, given that it was really true. The probability of rejecting the null given that it was true. Now, in fact, the more specific way is, in this fact, the probability of rejecting whatever we rejected in favor of the alternative given the null was true. Okay? And then a type 2 error, and I know people get confused on memorizing these things. I'm not sure why that is, but I want to, on a type 2 error, well, first off, type 1 has one word. We reject. All right, we reject, but that was an error. Because please remember, reject, it was error. Here, it was an error, but it was because we failed to reject. And please note, type 2, fail to. So the probability of failing to reject the null, given that the null is false. And yes, even in my crazy English, I know that that's not the way you spell to, but there you go. This conditional probability is an error. We accepted the null when we should have rejected null and accepted the alternative. So in this case, the probability of accepting the null given that the null was false. Probability that we didn't say OJ was guilty when in fact he was. All right? Yes, I pick on OJ a lot.
Why do we?
Go ahead.
Why do we say accepting the null instead of failing to reject?
Okay, because we did accept the null. You could say, I mean, if you wanted to, okay, if you wanted to say failing to reject, wow, failing to reject right here. So the probability of failing to reject the null given, that's probably even a better phrase. We don't accept the alternative. Sometimes we accept the null, okay? But if you want to say failing to reject, that's better statistical language. It really is. But it's okay. Well, it's not that it's okay, but sometimes we do accept the null. We try not to accept the alternative. All right, even though it says up there. Okay, does that help a little bit?
Yeah, I was just confused because I remember reading that you don't like actually accept it. You just like
Failed to reject it. You are
Yeah.
right. You are correct. We don't really accept it, but we failed to reject it. All right. And so that it would be statistically better to use the phrase failing to reject for sure. Okay? I like that. Okay. So, a couple FRQ problems. Now, I'll be perfectly honest with you. I think these are more challenging. Well, on the challenging side, on average, I think these are more challenging. This one is not particularly long, but I do think it's a little more challenging. And we will do some long ones too. But here we go. So a bottle filling machine is set to dispense 12.1 fluid ounces into juice bottles to ensure that the machine is filling accurately. Every hour, a worker randomly selects 4 bottles filled by the machine. So they're telling us, oh, okay, N is 4, size is 4, filled by the machine during the past hour and measures the contents. If there's convincing evidence that the standard deviation is greater than 0.05, the machine is shut down. Well, that's different. I don't think he ever told us how to test standard deviations. And the fact of the matter is, I didn't. That's called ANOVA, analysis of variance. It's not part of this course. However, they're referring to it here. It can be assumed that the amount of juice that is dispensed in the bottles is normally distributed. All right. Well, why did they have to tell us it was normally distributed? Well, they didn't give me a list of data, so I cannot test. I cannot draw a box plot to check for normality. And N is less than 30, so it's not normal by central limit theorem. So I needed to know that the underlying population was in fact normal. During 1 hour, the mean number of fluid ounces of the 4 bottles selected was 12.05. Okay, so this is my X bar. And the standard deviation was 0.085. That's interesting, because I think they told me they wanted it to be 0.05 up here, but it's not. Okay, so perform a test of significance to determine whether the mean amount of juice dispensed is different from 12.1 ounces. They tell me different. So that lets me know that I'm working with not equal. Assume the conditions for inferences are met. And we all go, yay, I don't have to do my conditions this time. All right, had I written my conditions, well, we'll talk about that in just a second. So the first thing, let's go ahead and write our null and alternative hypothesis. So HO, they say it's set to dispense 12.1 ounces, and they want to see if it's different from 12.1. So mu equals 12.1. Please make sure this is a Greek letter. If you use X bar here, you lose a point. Just that it's simple. The alternative, mu does not equal 12.1 ounces. All right, need to define our variable. Mu equals the true population mean of juice dispensed. All right, now we don't have to do the conditions, but I'm going to do them here anyway. So my conditions, the first one, random sample. You can't just write random sample check, or they don't like that. They much prefer you to say random sample given in the problem. All right. 2, N is less than 10%. So in this case, 4 divided by 0.1 equals 40. Reasonable to assume that there are at least 40 bottles of juice produced an hour. I'm sure they produce thousands in an hour. And the third one is our normal condition. And it was given in the problem. So those would have been my conditions here. All right, so the next thing I need to do is I've written the hypothesis statements. I've defined my variable. I've done my conditions. I need to write my formula. Well, this is a one sample t, so t equals x bar minus mu s divided by the square root of n. And in this case, we know x bar is 12. So I should draw my little picture so I can kind of look at what we're working with. So this is 12.1. And I ended up with 12.05. All right, this is a not equal situation. So I'm going to always shade in the direction farther away. Because remember, p-value is the probabilities as extreme or more extreme. So I'm going to shade in this direction. All right? So p is less than 12.05 minus 12 over 0.085 divided by the square root of 4. Now, there's something not quite right about what I just finished writing. I'm sorry I didn't have that on screen. How many tails are there? Well, there are 2 tails, so I need a 2 out there. All right, so at this point, I have my x bar, I have my mean, I have my sample standard deviation, and I have my sample size. Second, stat, test, simple t-test. We're using statistics this time, so that needs to be highlighted. Our mean is 12. Our x bar is 12.05. And our standard deviation is 0.085, and our sample size is 4. This is not equal. And by the way, I left off something. I forgot to address this. I have a problem with this. Degrees of freedom is 4 minus 1, which equals 3. All right? So I end up with 2 times the probability that t is less than 1.176 equals 0.324. Now, I don't know about you, but to me, that's not very rare. So that's 32% of the time. Not half, but it's not that bad. So 0.324, this is p-value. This is alpha, this is 0.05. Excuse me, this is greater than. So fail to reject. So now we need to write our conclusion. Our p-value is 0.324. We fail to reject the null. There is not sufficient evidence at alpha equal 0.05 to suggest that the true population mean distribution of juice distributed is less than 12.1 ounces. Our p-value is 0.324. We fail to reject the null. There's not sufficient evidence at alpha equal 0.5 to suggest that the true population mean of juice distributed is less than 12.1 ounces. That word should not be there. Okay?
Isn't it is it
I'm sorry, I didn't catch that.
isn't it not equal to 12 point?
Yes, is not equal, or I'm going to use my favorite word for this is different.
Okay.
Than, but you could have definitely said not equal to. That's fine. Thank you for catching me on that. I should have referred straight up to my alternative hypothesis, and I did not do that. The true population mean, to suggest the true population mean is different than 12 point, let's rewrite. I'm going to rewrite that. I'm just going to rewrite that. That's really bad. So our p value is 0.324. We fail to reject the null. There is not sufficient evidence at alpha equal 0.05 to suggest that the true population mean amount of juice is different than 12.1 ounces. Thank you for catching me on that. I appreciate it. So does everyone who's watching, who ends up watching the video and gets confused. So thank you for that. Okay, any questions on that other than why did the teacher make a mistake? Because he's human and tired. All right. Now we get into this trickier part. And I really wouldn't be surprised if they did something like this where they brought some sort of simulation into the situation. Oh, you know what? There's one thing I want to talk to you before I go into that about this particular problem. And I want you all to get used to thinking about what the population is that they were trying to generalize to. And when I read this, it's not they're generalizing, they want to generalize this to the juice, the amount of juice put in bottles in a particular plant, but they're actually looking at specific hours. So they're basically the amount of juice put in the plant, put in a bottle during a particular hour. So it sounds like to me that they're doing tests every single hour to check to make sure that they're getting enough juice in the bottles. That's the way it appears to me. And so I would say, hey, my population that I'm trying to generalize to is the amount of juice put in a bottle at this plant on a specific hour. Okay, I'm not generalizing it to all the juice at the plant, just that 1 hour. So, like I said, I wouldn't be surprised if they brought some sort of interpretation of simulation. It seems like they're asking more of these questions. So I wouldn't be surprised if this happens. So to determine whether this sample of 4 bottles provides convincing evidence the standard deviation is greater than 0.05. Remember, in the problem stem at the very top, they told us, hey, if it's greater than 0.05, they shut down for recalibration. All right, so they want to know if it's greater than 0.05, and they actually calculated a value of 0.085 is their standard deviation, which just looking at it, I'm like, hey, there appears to be evidence that is greater than 0.05. Why? Because the value is. The question is, how often does that happen? I mean, could that be random chance? Did I just get a bad sample? All right. So to figure that out, it's like, hey, you know what? We looked at this 0.085. It's bigger. Let's run a simulation to determine whether or not this is weird. Do we need to be concerned, or does this happen by random chance? Like, oh, just a bad sample. All right. So in the simulation study, 300 samples, each of size 4, were randomly generated from a normal population with a mean of 12.1 and a standard deviation of 0.05. So basically, they ran a simulation. They said, you know what? This is what the mean is supposed to be, and the population standard deviation is 0.05. And they ran the simulation, and they go, well, how often do we get a standard deviation of 0.085? That, you know, how often does that happen? So the sample standard deviation was computed for each of the 300 samples. The dot plot shows the sample standard deviation. So this is what they expected, and they get this range. Sometimes they had very, very small sample standard deviations, and sometimes they had very large sample standard deviations. But we're not concerned about the small ones, because they said, what's the probability that it is greater than 0.085? Well, when I look at this chart, I'm going, you know what? That looks about where 0.08 is, because that's 0.08, that's 0.09, so right in the middle is 0.085. Well, okay, that's good, because I really didn't want to count all 300 of those dots. But I can look it over here, and I go 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it looks like it happened 12 times out of 300. So 12 out of 300. So about 4% of the time. I should have done that in my head. So it happens about 4% of the time. I don't know about you, but 4% of the time seems fairly unlikely. So, so basically this right here is essentially a p-value. Now, it was a p-value that was created not by a hypothesis test, but through a simulation. And our alpha was essentially, if we set it at 0.05, this is less. So with that being the case, we're going to reject. Well, what was our null? We didn't set it up, and you didn't have to set it up. But this might help you from an understanding standpoint. From an understanding standpoint, we would say 0.05. The alternative was greater than 0.05. Now, we didn't need to show that. You don't need to define it because you didn't need to show it. But we're going to reject the claim that the standard deviation is 0.05. So here's what I would say. And you wouldn't have had to write it out just the way, like, you wouldn't have had to say all of it. You would not have had to include that last statement necessarily, but you need to answer the question. And what was the question? Well, is it greater than 0.05? Our simulation indicates that the machine has a standard deviation greater than 5. Well, now we just answered the question. Well, I need to go a little bit further and explain that by giving a p-value, or at least that's what I would do. And we know that our p-value is about 0.04. So there is a 4% chance of getting a sample of 0.085 given that the machine was operating at a standard deviation equal to 0.05. So there's a 4% chance of getting a sample of 0.085 given the machine was operating at an alpha of or at a standard deviation of 0.05 or a sigma of 0.05. And if you didn't say it like this, word for word, that was fine. But that's what's happening. This is essentially a p-value, and basically our simulation says, hey, there's only a 4% chance we get a sample like this. So we don't believe it's operating. So you need to say that it's not operating, that it's not operated greater than 0.05. You need to make sure that you say that it's not operating at 0.05, that it's operating at greater than 0.05 because there's a 4% chance of getting a sample like this. If you said it's something along those lines, you would have received full credit. Okay? Now, that's kind of a twisted question. And like I said, a more difficult one to respond to, especially when they throw in standard deviation, which is not which is not a test for standard deviation, which we don't learn how to do in this course. So, questions on that particular problem? All right. Now, this year they say there's no investigative task. And this question 6 is our investigative task. I feel like this might be a fair type question for them to ask, even though it is an investigative task. They are longer. Investigative tasks, you're supposed to plan on about 25 minutes to take. And so this would be a good example of what a 25-minute question might look like. And I don't think this one is as big a stretch as some of their investigative tasks. So regulations require that product labels on containers of food that are available for sale to the public accurately state the amount of food in those containers. Specifically, if milk containers are labeled to have 128 fluid ounces and the mean number of fluid ounces of milk in the container is at least 128, the milk processor is considered to be in compliance. All right? So basically what they just said there is if you say it has 128 ounces, it better have at least 128. All right? The filling machines can be set to the labeled amount. Variability in the filling process causes the actual content of the containers to be normally distributed. That's good to know. A random sample, there's another good word, of 12 containers of milk was drawn from the milk processing line in the plant, and the amount of milk in each container was recorded. So we've taken a small sample, and so central limit theorem wouldn't apply, but they tell me it's normally distributed. All right? The sample mean, the standard deviation of the sample of the 12 containers was 127.2. That's an issue because we're supposed to be at 128. So it looks like there might be a problem. 28 and 2.1 ounces respectively. Now they're telling me this is a standard deviation of the sample. And because this is a standard deviation of the sample, then I am working with a t-test as opposed to z. Is there sufficient evidence to conclude that the packaging plant is not in compliance with regulation? Provide statistical justification for your answer. Well, so basically they ask for evidence, and I'm sitting there going, just looking at it, there's some evidence because 127.2 is less than the 128 that was required. But whenever they ask for evidence, typically speaking, you're going to run a hypothesis test. Could you do a confidence interval? Yes, but generally speaking, they will tell you a confidence level or say run an interval if they want one. So most of the time when you say, is there sufficient evidence, they're asking for you to run a hypothesis test. So that's what we're going to do here. All right, so first off, my null hypothesis is that the machine is doing what it's supposed to, and what it's supposed to do is have 128 ounces. My alternative, I'm not too concerned if it's producing more than 128 ounces, or at least from meeting regulations. I'm concerned if it's doing less than 128 ounces. And while I have a moment and I'm thinking about it, I'll draw my picture. We're at 128. Our X bar is 127.2. And we're shading in that direction. All right. Need to define our mean. Mean is the true population mean amount of milk being dispensed. All right. All right, conditions. 1, random sample. And that was given in the problem. Second condition, N has to be less than 10%. So in this case, 12 divided by 0.1 equals 120. Reasonable to assume that there are at least 120 containers of milk. Third one, they made it easy for us. Normality given in the problem. All right, so we're going to be running a hypothesis test because they said calculate evidence, and they told me the sample mean. So this tells me that I have an X bar. So T equals X bar minus mu S divided by square root of N. So probability that T is less than, based on my graph, 127.2 minus 128 over 2.1. Don't forget to put it over the sample size, which is 12. All right, so in the calculator, stat, test, t-test, mean of 128, standard deviation of 127.2, not standard deviation, I mean, excuse me, sample mean of 127.2, standard deviation of 2.1, sample size of 12, and make sure we have the less than highlighted. So the probability that t is less than negative 1.32 equals 0.106. All right, that's a larger p-value than I would have expected for that, but that is what's correct. So our p-value compared to alpha, 0.1069 is greater than 0.05. So we fail to reject. All right, our conclusion. Our p-value is 0.1069. We fail to reject the null. There is not sufficient evidence at alpha equals 0.05 to suggest that the true population mean amount of milk is less than 128 ounces. Now, what's interesting about this is there's not significant evidence to say that the average amount is less than 128 ounces, but we certainly know that based on this, we have some bottles that are less than 128 because we ended up getting we ended up having a sample mean of 127. So obviously it's producing some below 128, but on average, we're still producing at 128. Okay, so continuing on to part B. By the way, some years they grade things in crazy ways. Normally speaking, if they make you run an entire hypothesis test like we just did, that's going to be about 2 points or so, or more. And on this particular year, part A was only worth a single point, which was horrible, in my opinion. I think that's way too much work for a single point, but that's what it was on that particular year. So inspectors decide to study a particular filling machine within this plant further. So like, hey, we're gonna look at this particular machine. For this machine, the amount of milk in the containers has a mean of 128 and a standard deviation of 2 fluid ounces. What's the probability a randomly selected container filled by the machine contains at least 125 ounces? All right, so what we're looking for is the probability that X is greater than 125, okay? By the way, is that a typo on my part? Hold on just a moment. That might be a typo. No, it is not a typo. All right. So, and one thing to keep in mind about the College Board when they do things, they oftentimes try to lead you through a problem a little bit to help you out. So one part's supposed to not just be used, it's supposed to be helpful. And part B is going to be useful further down. So here we go. So what's probably randomly at least 125? Well, here we're only looking for one container. Excuse me. All right. So, and we know that we have a standard deviation of this. So this is going to be a Z. So Z equals X minus mu over sigma. So the probability, I should draw my picture. It'll help me out too. 128. This is at 125. And I should be shading up like that. Well, right away, I should be looking at that and going, hey, you know what? This should be more than 50%. So probability that 125, probability that Z is greater than 125 minus 128 over 2. Second vars, normal CDF, lower, based on my chart, my drawing is 125, upper 128, upper infinity, mean of 128, standard deviation of 2, and I get a value of 0.9332. All right, I also would like to run this slightly different. If I'd gone to stats test and ran this as a z-test, my mean is 128, my standard deviation is 2. My x bar is actually just a singular value, but it's still 125. But my sample size is size 1. And if I go to calculate, I end up with the probability that z is greater than negative 1.5 equals 0.9332. The benefit of going this way is it gives you the z value as well. All right. So in this case, there's about a 93% chance that we'd get a bottle greater than 125. So let's look at part C. In part C, an inspector will randomly select 12 containers filled by the machine and record the amount of milk in each. What's the probability the minimum or the smallest amount of milk recorded in the 12 containers will be at least 125? In order for the minimum to be at least 125 ounces, each of the 12 containers must contain at least 125 ounces. Well, what's the probability that one container contains 125 ounces? Like, oh, the probability of one is 0.9332. We just calculated that. All right. So now I need 1, 2, 3, all the way to 12, which tells me 0.9332 to the 12th power. So 0.9332 caret 12. And what I learn is if I had 12 containers, there's a less than a 50% chance that all 12 would have had the right amount. There's less than a 50% chance that all 12 would have had the right amount. Okay. All right. So B was worth 1, A was worth 1 point, B was worth 1 point, C was worth 1 point. And then we get to the simulation in part D. An analyst wants to use simulation to investigate the sampling distribution of the minimum. This analyst generates 150 samples, each consisting of 12 observations from a normal distribution with a mean of 128 and a standard deviation 2, and finds the minimum for each sample. The 150 minimums sorted from smallest to largest are shown on the next page. So basically, I have this page here with a whole lot of values. Hopefully you all have that on your screen somewhere or something. But anyway, because that's part of the notes. But each column it has 50 values. So 50, 100, 150 different values. And they've ordered them from smallest to largest. So the smallest was about 121 ounces, 121.45, and the largest of the 150 was 126.95. Okay. And he finds the minimum for each sample. The 150 minimums, sorted from smallest to largest, are shown on the next page. So what we were looking is not at the average of each sample. They said, hey, we're going to run samples of 12, and we're going to record the smallest value from each sample. So that's what they did. They recorded the smallest value from each sample. The next thing says, use a simulation to estimate the probability that was requested in part C and compare this to the theoretical value. All right. So the theoretical value that we calculated in part C was, I set it aside, 0.4369. That's what we calculated in part C. So I need to look at this thing and go, all right, where does 125? So I have 84 values out of the 150 that are not producing the right amount of milk. All right, the rest of them are. So if I have 150 minus the 84, I end up getting 66. All right, well, that was 66 out of 150. And I end up getting 0.44. So my simulation says that, hey, 44% of them have minimum values greater than 125 ounces. But that wasn't just, if I just wrote that and did that part correctly, I only got partial, because the other part of it was compare this estimate with the theoretical value. Well, my theoretical value is 0.4369. So I would just simply say my simulated value of 0.44 is very similar to the theoretical value of 0.4369. All right. So the simulated value of 0.44 is very similar to the theoretical value of 0.4369. So looks like a good simulation. If you didn't include that, that's fine. But to me, that simulation looks like it modeled what you expected to happen very, very well.